Welcome to this video in which we will explain globally how the DFT works. We can obtain the frequency content of a signal by using a Fourier transform. In the previous video we've seen that the DFT is an algorithm with which we can calculate a sampled version of the Fourier transform on a computer, and the definition of the DFT is given in the equation. So the DFT transforms n, capital letter N, samples of the discrete time signal xn into n values xk, which represent the sampled version of the frequency content of the samples xn. The DFT index k is related to the relative frequency theta is k times 2 pi divided by n. Because of the fact that we use samples in time domain, the resulting frequency content will be repeated. So in fact the DFT frequency index k ranges from minus until plus infinity. We only need one so-called fundamental interval of n frequency samples. Usually we use the samples k is 0 until k is n minus 1. These samples are used for the inverse DFT, which is defined in the given equation. Now the same reasoning as before applies. Because of the fact that we use samples in the frequency domain, the resulting time domain sequence will be repeated. Although we start the DFT calculation with n samples of the time domain signal xn, the result of this repetition that in fact the time index n ranges from minus to plus infinity. It's obvious that only one period of n samples is needed for the DFT calculations. For this, we use the original samples with time index n ranging from n is 0 until n is n minus 1, the so-called fundamental period, abbreviated as FP. Concluding, it follows that the DFT has a periodic behavior. In a follow-up video, we will discuss the implications of this periodic behavior. In this video, the main focus is on the DFT. The only differences of the inverse DFT with the DFT are: the minus sign in the complex exponent has been interchanged by a positive sign. In this video we will see that in the summation we add complex factors which turn clockwise. The positive sign results in the addition of complex factors that turn anti-clockwise, while the procedure is the same. All Fourier transforms, including the DFT, preserve energy. This means the energy in both time and frequency domain stays the same. Thus the Fourier transform cannot add energy when going from one domain to the other. For this reason, it can be shown that we need a factor 1 over n in the inverse DFT definition. Now let's look to a very simple example in which we calculate the 4-point DFT of a discrete time signal, from which the samples xn can be described by the equation xn is cosine pi over 2n. In the 4-point DFT summation we only need the 4 samples x0 until x3. For the simple example, only x0 is 1 and x2 is minus 1. While the other two samples are 0. By using the fact that e to the power minus j pi k is minus 1 to the power k, the result equals xk is 1 minus 1 to the power of k. If we evaluate this expression for all values of k, it leads to 0 except for k is plus or minus 1, plus or minus 3, etc. In general, we can describe such a function by discrete time delta pulses. The modular function mod 4 represents the repetitions of the DFT length n is 4 in this case. Since we only need one repetition, which in the DFT case is usually chosen for the index range k is 0 until n minus 1, we obtain in the fundamental interval the following values. x0 is equal to x2 is equal to 0, and x1 is equal to x3 is equal to 2. So the frequency constant has two peaks which represent the discrete time phasor components of the original signal samples. Xn is cosine pi over 2n. Now, in order to understand the mathematics that are used in the DFT algorithm, we will see that the exponent e to the power j 2 pi divided by n plays a very important role. That's why this exponent is given a special name, the Twiddle factor. This Twiddle factor is used in the DFT summation, in which the relative frequency theta is related to the DFT index k as k times 2 pi divided by n. Since the summation index is n, the resulting sum is a function of the DFT index k. Thus, in the summation we add n, capital letter N, terms of the discrete time phasor with relative frequency k times 2 pi divided by n. In the following animations we will show how this Twiddle factor acts in the DFT summation. In the first animation we show one period of n is 20 samples of the discrete time phasor with relative frequency theta is 2 pi divided by n is 0.1 pi. The projection on the real and imaginary axis are also given. Positive valued samples are depicted in blue and negative valued samples in red. If we take the summation over one period of n is 20 samples, we see that both real and imaginary parts add up to 0. In other words, the summation over one period of n is 20 samples of the discrete time phasor with relative frequency theta is 0.1 pi results in 0. It's obvious that the result is the same if we use the negative frequency theta is minus 0.1 pi. In this case, the vector turns clockwise. In this animation, we show the result for a phasor with relative frequency theta is 2 times 2 pi divided by n is 0.2 pi. If we take the summation over n is 20 samples, the result is again 0. It's obvious that the result is always 0 as long as we take the summation over an integer number of periods of the discrete time phasor. There are exceptions to this rule, and the first exception is given in the following animation. Here we use a phasor with relative frequency theta is 0 times 2 pi over n is 0. Now the discrete time phasor, which writes as e to the power j 0n, maps for any time index n to the same value 1. Thus it maps to 1 on the real axis and 0 on the imaginary axis. And from this it follows that the summation adds up to n, which equals 20 in this case. A similar reasoning follows when the relative phasor frequency equals theta is n times 2 pi divided by n is 2 pi. For this case, the phasor writes as e to the power j 2 pi n. So the phasor maps again for any time index n to the same value 1 on the real axis and 0 on the imaginary axis, and the summation adds up to 20 again. This reasoning holds for any phasor frequency which equals an integer number times 2 pi divided by n, since the phasor maps to the same value 1 on the real axis and 0 on the imaginary axis, and the summation adds up to n is 20. From this animation we obtain the following basic DFT summation property. The given summation is always equal to 0, except for the case that the DFT index case is an n-fold. Thus, for k is equal to 0, plus or minus n, or plus or minus 2n, etc., etc., which can be described by the given delta function in which the index contains the modulo n operator. In the following example, we will show that this basic DFT summation property is used in the DFT algorithm to find which frequencies are present in the n samples of signal xn. By applying the DFT operation to the signal samples xn, we try to find the relative frequencies which are hidden in the signal samples xn. In this example, we will use a DFT of length 4. So for each resulting DFT index k, the result of the DFT operation describes how much of the relative frequency k times 2 pi divided by 4 is contained in the signal samples xn in the range n is 0 until n is 3. In order to show how this works, we use again the same sinusoidal example as before, namely xn is cosine pi over 2n. By using Euler, we can split the cosine into two discrete time phasors. Then we split the summation into two separate summations and combine in each of these summations the complex exponents. Now we can use for each of these individual summations the previous described basic DFT summation property. The first summation will always result into 0, except for the case when the DFT frequency index k-1 is a 4-fold. Thus, for k is 1, or k is 5, or k is -3, etc. Mathematically, this can be described by the given delta function from which the index contains a modulo 4 operation. The second summation will always result into 0, except for the case when the DFT frequency index k plus 1 is a 4-fold. Thus, for k is -1, k is -5, k is 3, etc., which results in the given delta function. In the fundamental interval, which ranges from frequency index k is 0 until k is 3, in this case, this leads to the same two delta pulses as we found before. This example shows that indeed the basic DFT summation property is used in the DFT algorithm to extract the frequency components of the n signal samples xn. A similar result is shown in the following animation. In this animation, the input signal xn is equal to 4 cosine 2 pi over 7n, and the DFT length is 7. The cosine consists of two phasors, one phasor with positive and the other one with negative frequency 2 pi over 7. In order to simplify the figures, we only plot the phasor with positive frequency, which is shown in the left-hand side of the figure in blue. The figure in the middle shows the projection of this phasor on the imaginary axis. The figure at the right-hand side will show the result of the DFT calculations with different test phasors, which are depicted in green in the figure at the left-hand side of the plot. The first test frequency has been chosen as 0 times 2 pi over 7. When summing the result of the product of the green test and blue samples, the result is 0. Indeed, signal xn does not contain frequency 0. The next test frequency is 1 times 2 pi over 7. Now we clearly see the green and blue phasor frequencies are synchronized. The result of the summation of the product is positive, which implies xn contains the frequency 1 times 2 pi over 7, as can be seen in the frequency plot at the right-hand side. The next test frequency, 2 times 2 pi over 7 and 3 times 2 pi over 7 are not present in xn. Thus the summation of the product results in 0, as can be seen in the frequency plot at the right-hand side of the figure. When testing with negative test frequencies, it's obvious that we obtain similar results. In this animation, the input signal contains two frequencies, namely xn is 4 cosine 2 pi over 7n plus 2 cosine 2 pi over 7 3n. The left-hand figure shows the phasor components of xn with frequency 2 pi over 7 and amplitude 2 in blue, and the phasor 2 pi over 7 times 3 and amplitude 1 in brown. These phasors are added and only the result of the projection on the imaginary axis is shown. The test phasor is again shown in green. When performing the different steps of the test frequency, the results are as follows. The right-hand side shows indeed the expected frequency components of signal xn. In this video we've shown how the DFT works. Some topics that will be discussed in follow-up videos are: what happens if the periodicity of the signal samples xn is not equal to the DFT length n? Furthermore, we will see what happens if we calculate the DFT of a signal that's not periodic. We will show how we can perform a convolution, a filter operation, with the aid of a DFT. In many practical situations, the number of samples of the signal of interest can be much larger than n. How can we apply a DFT in such cases? A very efficient implementation of the DFT is the so-called fast Fourier transform, abbreviated as FFT. Together with the convolution property, this is the main reason for the existence of the DFT. This ends this video in which we showed how the DFT works. Thank you for your attention.